One important part of process planning is setting up all the inspection procedures in order to reconcile the parts and the features that we produce with the original design specification. So how do we know if a manufactured part is within the tolerance specifications and therefore is a good part? And what type of gauging could we use given the types of part features that we have? And then finally, what do we mean by a functional gauge that tells us something about whether or not this part is within specifications? Well, when we think about gauging, we are trying to create some type of a device, whether it is a physical device or a virtual device. By virtual, we mean a computational approach to gauging, and we'll evaluate part feature geometry. In order to determine what that gauging should look like, we have to understand the part features and then look at the various characteristics depending upon the dimensional and geometric tolerances that we understand from the design specification. So here you see some classical block gauges. These are physical gauges that are used to determine whether or not a part is within dimensional tolerances. The types of gauges that we'll be concerned about are, first of all, the dimensional, because those will tell us whether or not we are within the dimensional tolerances. And then shape and form tolerances corresponding, again, to the shape and form that we had with our geometric tolerances. Then our orientation, what angle is the part feature at, and then finally the position, where is that feature located. Well, it goes back to this notion of an envelope. And first of all, we start with the material condition envelope. If we can determine that the tolerance is based on a material condition envelope, then we're dealing with a feature of size. And that implies that there is a dimensional tolerance there. We might also have geometric tolerances that use an envelope as well. So we'll construct an envelope. Again, we're talking about hard gauging here, so it would be constructing an actual physical envelope. And that will be based on the idealized part, and when we think about that envelope, it's at nominal. So here's an approach to hard gauging. Let's represent the material condition envelope that's specified in our design. For features of size, it's very simple. We'll create two limit gauges. So you've probably heard of go and no-go gauges. The go gauge is always designed for the MMC envelope, and the no-go gauge is designed for the LMC envelope. Again, these would be specified in your design spec. We would look at the dimensional tolerances, and then we would know which one of these gauges to select. And of course, these are off the shelf, so we can purchase these and then use them based upon the envelope that's specified. For the geometric tolerances, we're going to use a virtual condition envelope, and we'll look at that a little bit later. So if I'm checking a feature of size, I'm going to create my go gauge, as we said, from the MMC dimension. And when I do that, essentially what you're checking for is whether or not this feature will assemble to another feature. So we're checking for assemblability. If the design was a valid design, then at MMC, the part is guaranteed to assemble. The no-go gauge, we're checking LMC. And LMC is looking more at the functionality aspect, because if our part is outside of LMC, then it implies that we're going to have an improper relationship between part features. Also note the nomenclature here in terms of go and no-go. The MMC, by go we mean it will insert into the part feature, and by no-go we mean that the gauge at LMC does not insert, because if it did, then that would mean we're outside the bounds of LMC. So again, the go gauge, if the part is good, the MMC gauge will insert into that feature, assuming again it's an internal feature. And the no-go gauge will not insert, meaning that we're between MMC and LMC. Of course, the disadvantage, as we see already with the hard gauging, is we don't know the actual dimension. We only know that it is within tolerances. So here's the basis for the gauge dimensions. As you can see, I've got a part on the left with an internal feature, and then I've got a part here that's going to be assembled to that part. We said before that the minimum clearance is based on the MMC for the two parts, so that if I'm going to have clearance around this surface, this difference here has to be positive. In other words, here's my part 1, here's my part 2. The MMC dimension for part 1 has to be larger than part 2, otherwise we're going to have a force fit. So there has to be a positive delta here, and that will be our minimum clearance. And then conversely, our maximum clearance will be the difference between LMC. So if we check both parts with a go gauge, so the go gauge for this one would be an internal feature, and then we would try to insert the part into that go gauge. Conversely, we would have a pin here corresponding to our go and no go gauge. Following the same rules, if these dimensions check out with our gauging, then we're guaranteed that it will assemble that we've seen before. I'm checking again the dimensional characteristics of this part. So we see, first of all, dimensional tolerances associated with the diameter of B and the diameter of the feature with the geometric tolerance. So I could use go and no-go gauges for those features. The hard gauges corresponding to my go and no-go gauges, we would select the MMC and the LMC dimensions. If we look at our design here, we note that LMC for B would be the smallest amount of material, which would be 8.0, and MMC would be the 8.1. And then for the feature that we're trying to control the perpendicularity of, the MMC would be the largest, which would be 3.6, and then the smallest LMC would be 3.5. So we would make, again, internal features in blocks here corresponding to our MMC and LMC, as you can see here, for the two. Now, this would require 4 gauges to check that part. How about a functional gauge for perpendicularity to determine whether or not that feature is perpendicular? Well, we're going to have to follow the same principles that we learned when we were dealing with datum reference frames and envelopes. So we need to establish datums. In this case, we want to make sure that that feature is perpendicular to A. So the gauge must include that datum reference frame when we're dealing with this functionality, as well as features for the actual part feature we're checking. So what we'll do is we'll start at the MMC dimension. Again, in this case, that would be the largest dimension. And then we're adding a tolerance zone by adding the tolerance zone size for external solid features. Conversely, if it's an internal feature, we're going to subtract the tolerance zone size, and that would correspond to holes. So we would make the corresponding pin actually smaller. So in this case, we started MMC of 3.6, going back to our design spec. So we would start at 3.6, and as we can see here, the tolerance zone size is 0.01. So that's what we use in terms of adding that to the size of that gauge. So we end up with 3.61. Note that we create an internal feature in this gauge. And that internal feature is meant to enclose this part feature over the length of the part feature. We also have an internal feature for B, and we have a separate component of the gauge that establishes datum A. So it's a two-component gauge. Obviously, this surface of our part has to make contact with A first in order to be consistent with our design spec. Now, here's the problem with that gauge design. What if the shaft is close to the LMC dimension? So in this case, we'll say that LMC is 3.5. So what if we have an actual dimension of 3.51, as we can see in this example? what will be the effect of that? Well, if I look at my tolerance zone, essentially we're saying it would be 0.01 plus the difference between maximum material condition and this actual dimension. Because, again, we're creating our gauge at 3.61. So, in effect, the width of our tolerance zone is 0.1. But what is the actual size of the tolerance zone? That would be 0.01. So by creating a gauge in that fashion, we've actually biased our result, and we would be accepting more parts, but of course they would have problems when we actually try to assemble them with other parts. So that is a definite problem. So what's the resolution here? Well, if we add MMC to our tolerance zone specification, then what we're saying, as we've indicated before, we're going to add the additional tolerance depending upon the difference between MMC and the actual diameter. So now our tolerance zone reflects what is happening in our gauge. And that's why you see the use of this MMC here quite often, because we're allowing additional tolerance as we deviate from material condition. So hard gauging can be used for our geometric tolerance zone specifications, but it's limited to those specifications that use MMC in the geometric tolerance. And our hard gauging is limited to a subset of our geometric tolerances. Let's look at a position of that feature with respect to our datum reference frame. Again, we see our M here indicating that we can deviate from maximum material condition, and now we're using both datum A and datum B as our datum reference. So I'll have to determine where datum B is with respect to datum A so that my datum reference frame can be established as a plane and a line perpendicular to that. And then we're going to position our tolerance zone, center it on B, and it will have a width of 0.01 plus any deviation from maximum material condition. Well, our hard gauges are exactly the same, so that hasn't changed. That's based on the dimensional characteristics. We still need 4. Now, if we want to check for our position with a hard gauge, or what we call a functional gauge, we have to include the datum reference frame and the part feature. So again, we'll start at the MMC dimension, and we will add our width of our tolerance zone to that because we have an external feature here. So we end up, as in the previous example, with our gauge having an internal feature of diameter 3.61. We also have the internal feature here meant to establish B, and we have the same feature, which is a separate component, used to establish datum A. On the left here, you see the mating envelopes that are required. We need to determine the surface for A, and then we need a mating envelope to determine B. The question is, what size is that? In other words, what size should we make this internal feature in order to accommodate our parts? Well, we have a similar problem as in the previous example, only now the problem is not the feature itself, but it is the contribution of datum B. So what if datum B, which is a feature of size, is close to its LMC dimension? And here we see this red region here indicating that we are at least material condition versus maximum material condition, again for datum B. Well, we've already accounted for the fact that our feature can deviate from its maximum material condition, which would give us 0.01 plus our difference between 3.6 MMC and our actual 3.51. So we have an additional 0.09 tolerance available there. However, we also have the potential for this deviation as seen here from our maximum material condition, and if it happens to be 8.1 versus 8, then we're going to end up with a tolerance zone width of 0.2 in reality with this gauge that we've created. However, the original design did not take into account this possible deviation in B. So our tolerance zone is still the original 0.01 plus deviation from the part features material condition. And now we've biased the size of the tolerance zone. In other words, we're going to accept parts, again, that will not assemble later on. That's going to be a problem. So how do we resolve that? Well, similar to what we did with the part feature, if we have a feature of size, in order to use a hard gauge, what we're going to have to do is add our MMC condition to the tolerance specification. So here you can see B now has an M, indicating that we will allow additional deviations if we deviate from 8.1 for B. Once we do that, then we resolve this problem with the tolerance zone size not being consistent with the design specification. So conclusion here again is you can use hard gauging for geometric tolerance specifications, but it's going to be limited to only those design specs where MMC is specified for the part feature, and we're dealing with, as well as datums, we're dealing with features of size. So if that is not the case, then you can immediately rule out the use of your functional gauges for the geometric tolerances. So we've learned that we need to consider again the material condition envelope, the virtual condition envelope, and that is for the geometric tolerances. So we created this virtual condition envelope corresponding to the physical gauge. We understand that a go gauge is at MMC, no-go gauge, LMC, and there's certain limitations to what you can do with the hard gauging with respect to geometric tolerances. We use gauging to evaluate our actual part features and determine if they are within the tolerances. And our functional gauges as well as go gauges can be used to check features, but they're limited in terms of the scope and applicability to geometric tolerances, as we'll see. Gauges are going to be constructed based upon our material condition, MMC or LMC, or the virtual condition envelope that we saw with our functional gauges corresponding to perpendicularity and position.